Imagine a world where our natural everyday movements became a source for endless electricity. In a world constantly on the lookout for sustainable energy solutions, the answer quite literally might be at our fingertips. First, let's understand what piezoelectricity actually is. It's the property of certain materials to generate a charge when subjected to mechanical stress. The inverse is also true, which means that you can put an electrical charge into piezoelectric materials and they can create a mechanical motion. Common materials exhibiting this property include quartz, Rochelle salt, cane sugar, and even bone. When looking at the silicon and oxygen molecules seems complicated, but as you rotate them, you find different symmetries. We need to understand this hexagonal shape. The red represents silicon and gold oxygen. The oxygens are a bit negatively charged and silicon's positive. Watch what happens at the center when you compress the crystals. The two side silicons move out and bottom moves up. So the average position of these three charges moves up slightly. And similarly, the two side negative charges move out, but the top moves down. We have a neutral center when you compress the crystal, and this creates a polarization of the material, enabling it to generate an electric field. In order to learn more about the potential of piezoelectricity in future wearable electronics, I built a piezoelectric glove using two PCT strips as piezoelectric sensors placed on the middle and pinky fingers. Using finger contractions from actions like twisting a ball, I was able to light up 3 different LED colors and obtain a peak voltage of 4.08 volts of alternating current. As you can see from the multimeter reading, I was able to get quite a bit of voltage, up to 1.2 volts on my multimeter. So what does this mean in technology? Well, this glove is a minor representation of the application of piezoelectricity in devices. For example, this exoskeleton that was built. The use of piezoelectric materials in exoskeletons allows for energy harvesting from joint movements, which can be used to power the exoskeleton or the devices. So, what are the benefits and drawbacks of piezoelectricity? One of the benefits of piezoelectricity is due to its adaptability. Picture a world with off-the-grid power where we can optimize piezoelectric devices to detect all sorts of stimuli to power everything, like an electric stroller powered by squeezing the bars, a fan powered by one's weight on the bed, or a school powered by students mumbling conversations and footsteps on the tiles. Unlike solar and wind, piezoelectric devices generate energy from mechanical stress, which is a constant thing, so it's always generating as long as there's mechanical stress. Then, piezoelectricity can be easily scaled up or down based on the use. It can be scaled up for industrial uses or it can be scaled down for uses in the military devices. So what are the drawbacks of piezoelectricity? Firstly, piezoelectric materials can generate a fairly small voltage, which means that they require an impedance cable to connect them to an electrical interface. Additionally, these electric materials are affected by environmental conditions like temperature and humidity, which affect their performance. While in the static condition, you can't measure their output. In the tech world, piezoelectricity is being used in wearable devices for various uses, like energy harvesting, health monitoring, smart sensing and actuation, and because of its flexibility and lightweight design and communication and connectivity, it is able to be used in a multitude of different ways within wearable devices. We've only scratched the surface with the potential of piezoelectricity. The ability to harness energy from everyday movements opens up a world of possibilities for sustainable energy solutions and innovative wearable devices.